World Dutch Association of Engineers, Department Electrotechnical Engineers. Today the topic is DC systems in practice. This is how you do it. My name is Koos Koster and I will be your moderator for today. The technical support is by Paul van Moerkerke. First, some house rules. Please switch off your camera and your microphone. If you have any questions to the speaker, please put them forward through the chat facility in Teams, preferably in English, but can also be in Dutch. We will put the questions at the end of the presentation to the speaker. The session will be recorded and be published on our YouTube channel. If you watch this webinar, you agree with the recording and publishing. In short, I will tell you something about our association. We are the leading association of engineers in the Netherlands, and we are existing for more than 175 years. Our association is committed to the interests of engineers and technical professionals in the Netherlands and Netherlands overseas. Look further on KIVI.nl what we organize as an association, or even better, become a member of the largest engineering association in the Netherlands. Then you will stay informed of the latest technological developments about, for example, the energy transition, and you can participate for free in our lunch webinars in addition to all kinds of other activities. The subject of today, DC systems in practice. This is how you do it. Many countries are struggling with grid congestion problems because many assets such as PV charging and battery energy storage systems are natively based on direct current. Using direct current to connect them together is a logical choice. In addition, DC systems have been shown to reduce investment costs and footprint, as well as increase operational efficiency and reliability. I would like to give the stage to Dr. Engineer Pavel Burgat, Global Applications Engineer at ABP. In his presentation, he will deal with the topic, amongst others, why direct current offers a solution to many of the challenges we face today, and what we need for the safe and reliable operation of DC systems. Pavel, you can start your presentation now.
Thank you very much for the nice introduction, and also thank you for the opportunity to be with you here today. It's always a pleasure, and I apologize, I have to speak in English. There was time when I was studying in the Netherlands, but that's already a few years back, and my Dutch is no longer on the level that I could hold a full lecture speaking fluently. But now to the topic. So today I slightly renamed the presentation into direct current systems and their applications, because I think that's what's very important for us. The talk is split into 5 parts. Based on the discussion we had, I put a little bit more effort also on the first part, and that's explaining and maybe discussing why we are talking about the technology that's essentially 100 years old and what changed in the past years that this again becomes relevant. Then an illustrations of the applications and fields where DC is already growing quite fast. And the 2 sections are a little bit more technical that follow, number 3 and number 4. One is about the general knowledge about the DC systems and what needs to be considered. And with a little bit of more focus is on the protection and how can we make the DC systems more safe and reliable, so that people feel safe working with these systems. And 5th section is the shortest, but it gives some links and ideas for resources that can be found on these topics. So going ahead and asking the question, why DC? I think it's an important question to ask and also to answer, to understand the motivation. So one of the first things when we look at the power consumption and how it's evolving. So we have the traditional sectors like industry and buildings, and they are growing quite stably, and there is no big change. And we could do things as we are doing them today without much adjustment. But there are new segments such as transportation, data centers, and fuels like hydrogen that will be very important to decarbonize other parts of the society. And these new segments are growing very fast. And to satisfy this growth, we need to think about the new solutions. So we see that even in the more traditional electricity business, we have some segments that are changing very fast. This is on the load side. When we look at the generation side, this is a little bit more discussed topic, but still it's interesting to have a look at where we are currently in the changes of the generation mix. And we can see that over the past 20 years, already there is a significant change, seeing renewables growing from 16% in European Union to 38%, while the nuclear remain more or less stable or slightly declined. But what is for sure declining are the traditional fossil fuels, especially the coal. And it was already anticipated in the introduction. The sources such as solar, wind are slightly different in their nature than fossil fuels-based power plants. And third important piece of the puzzle is the battery energy storage. Now, battery energy storage maybe 5 or 10 years ago was not making headlines, but you can see that the growth over this decade is double digit. So that means we are really putting much more batteries into the grid. And what is maybe not shown here, this is also fueled by the fact that it's becoming much more economical. The prices of batteries dropped sharply over the last 10, 15 years and continue to drop. And to better illustrate how much of a progress was made in this area, I put 2 examples. In 2017, Elon Musk made headlines with saying that they will install 100 megawatt power storage with 129 megawatt hours of storage. Now, this made headlines, and also the time in which they deployed it, which was a little bit around half a year. Now, in 2025, in June, started a construction of probably the largest battery energy storage site yet, offering 1 gigawatt of power and 6 gigawatt hours of energy storage. Now, to put that into perspective, in 8 years, we increased the power 10 times and the energy 45 times, a little bit more than 45, as a matter of fact. When we compare that with other sources of power, for example, with the nuclear, we can have a look in Czech Republic, where they announced to have a new nuclear power plant of 1 gigawatt per reactor, and it will take 12 years to deploy it. The colleagues in Inner Mongolia, where they are deploying this battery energy storage, are estimating that it will take them 214 days to deploy this project. And this is why the renewables and batteries are such an important piece of the puzzle here. Not that they are just decarbonizing our grid, but it's also the speed at which we can deploy them. So when we look at the grid level, how does it look from the big picture? Here we are looking at a simplified picture of power system, starting at the generation side, going all the way to the consumption. Of course, in the middle, we have utility or distribution for the homes, and then transportation. Now you see that in the past, the generation side was represented by large rotating machines, and we didn't have much power electronics. Sometimes, of course, high voltage DC was utilized to connect distant parts, especially when the cable was laid underwater because of the capacity. So HVDC was there, power electronics was used, but it was very limited. Now, also on the load side, most loads were either machine or lights, so they were really resistive and inductive. When we look today, on the generation side, we have growing PV, growing wind, now interfaced through power electronics converters. We will have much more hydrogen in the grid in the coming years, and we already have a lot of storage collocated with the production of PV. Now, the collocation of storage with PV makes a lot of sense, but it also adds more power converters and their consequences of their switching into the grid. Similarly, in the utility side, in the distribution, we are adding storage to improve the power characteristics and the power stability. And on the load side, there is a big change. For example, in the factories, we are now using much more variable frequency drives because they are much more efficient than if we just interface the machine directly to the grid. We have completely new loads, data centers with their power demands now climbing, again, change the power shape. And in the transportation business, there is a complete revolution. Of course, we have electric vehicles, but we have also trains that are now having large batteries incorporated. In marine, we see the growth of the battery systems and the battery-powered ferries, e-buses, and soon enough, for example, you have a startup in Delft, Elysium, that is working on fully electric aircraft. But even putting aside fully electric aircraft, the aircrafts are also electrifying. So you can see one common theme is the growth of power electronics. And colleagues from Aalborg University estimated that approximately 70% of electricity is processed by power electronics. Now, this is a complete change to what we have seen 30 or 40 years ago. And I would also claim not many fields have grown so fast in such a short time. So what is the consequence when we have a grid that's dominated by power electronics converters? How does it look like? When we look at an AC power system that is predominantly based on sources interfaced through power electronics converters and loads and battery energy storage, we see that each time we go from natively DC source or energy storage, we need at least one or two conversions. We need a DC-DC conversion to adjust the voltages for the battery, for example. And then we have a DC bus, and then we need to make an AC. And this is sometimes more complicated than it looks because we need to synchronize on the grid, we need to adhere to the grid codes, and so on. So especially as we are getting to the grid edge, even though these systems are very resilient, very robust, we end up with many conversion stages and relatively complex system design. And what is a consequence of this complexity? We can take as an example the Netherlands. And honestly, I'm taking the Netherlands as an example mostly because there are not so many countries that have such a good database available publicly. But the situation is similar in many other countries. The map we are looking at is the capacity map. So this is, you can find it online at the link provided here. And it shows you where you can connect new loads. And similar map can be also made for where you can connect new sources. And these maps are regularly updated based on the information from both TSOs and DSOs. Now, as it's explained also on the web page, expanding the electricity grid is important, but it's quite slow and it's often not enough because we don't have enough space. So one thing is, as a consequence, is that temporarily we are not able to connect new loads. And then the question arises, okay, could we do something on the grid edge that could elevate this problem? And one of the solutions would be utilizing more DC on the grid edge. Why? Because effectively we are decoupling ourselves from the AC side. Now, using the DC bus, common DC bus, of course, we get rid of many conversion steps, as you can see in the picture. We are more effectively using the raw materials, so we need less copper because of the voltage rating. And the system design on the grid edge becomes somewhat simpler. It is true that some components of the DC systems are a little bit more complicated, but the system design should be simpler. You can think about this as a mobile phone evolution. In the past, when we had the wired phones, the system of the wires was extremely complicated. However, the phone itself was very simple. Today, when I have my phone, it is an extremely complicated device, but the cellular network is quite simple. So in a way, DC systems are like mobile phones. Ideally, they make our life on the system level easier. So what are some of the applications where DC is already used, and are they growing? So what are the trends? One of the early adopters of direct current solutions were vessels, especially smaller vessels like ferries or vessels operating in ports. one of the main reasons to look at DC in the past was in AC, we have large transformers, which of course on a vessel, they take space, add weight, and you try to save both. So the idea was, okay, if we go to DC, can we get rid of the large transformers? As it turned out, it's much more that you gain, not just getting rid of the transformers. It's easier to integrate battery energy storage. The fuel consumption is reduced and the entire system becomes a bit more reliable. Of course, what you need to think about is the protection. But already here we can see that we will be probably using the traditional protection devices. We have the fuses, we have switches, switch disconnectors, but also some new devices that I will be talking about later. So what the colleagues in marine showed over the last 10 years, or actually more, because the first DC vessel was released in 2013 by ABB, and it was Dynastar. And in that time, the DC systems in marine became often cheaper to acquire. They are for sure cheaper to run because of the fuel economics. And they proved to be more reliable because the system design is quite new and because the number of components is reduced. Now, marine is not the only application. In Germany, since 2017-18, there are several projects running with live pilots in automotive sector, so with actual DC installations in factories. And all these installations show that, first of all, having a DC bus for the loads with integrated energy storage allows significant reduction in peak power rating. Now, this is one of the very interesting results, especially when we have congestion problems in the grid. For applications that utilize many robots, machines, the recuperation of the braking energy becomes very interesting, and using DC, it becomes much more efficient. So this also increases the operating efficiency. And third, but not least, also the copper requirements were reduced when using DC, up to 35%, which is also an interesting result when you think that most of the copper mines are now dropping with their output, and likely copper is going to get much more expensive over next years. One of the other applications that I would say by large started in the Netherlands, we can think about the ABN AMRO building built by DC-systems today. But we have also the building at TU Delft, the Pulse building that is done with DC, is the residential sector. Here, one of the value propositions is that you can probably upgrade your system without touching the AC part, but you create a shared DC backbone for the PV and battery and some of the DC loads. Now, the DC loads could be, for example, lights, because LEDs are using DC, so you just need to adjust the voltage level. These systems, especially in the characteristics as drawn here, are getting very popular now in China, and they refer to them as PV, energy storage, DC, and flexibility. However, many similar systems have been realized, as I mentioned, in Europe, but also in US for energy communities in Florida, for example. And last but not least, once again, we have a comeback of data centers into DC. So the data centers were already interested in using direct current around 15 years ago. However, the efficiency gains 15 years ago were not that great to motivate further adoption. But today, the main change that is happening is that data centers are consuming much more power, especially the AI data centers. The racks are growing from what is now common 20 kilowatts to projected 1 megawatt by the end of the decade. Now, you can imagine that fueling such a large infrastructure will require quite a different approach. And this is why colleagues in data center business are now looking into the options that were developed in marine or in other applications, and if that could help them to reduce the footprint needed for the infrastructure in data center, as well as improve the operating efficiency, because of course the electricity consumption is one of the main OPEX drivers. So now a question, and of course we don't have a real poll, so you can just guess, let's say, But the question is, where do you think there are the most DC grids? Our colleagues in DSite, which is a software that I will talk about a bit later, they counted around 50 projects in Europe. Now you can see that China is quite empty. However, with the information we have about PDF and about the other projects that are running, the approximation is that there is approximately 200 DC grids already built there to date. So you can see that the number of DC projects in the world is growing steadily, if not with increasing speed. Moving on towards a little bit more technical part of the talk, I will start with some fundamentals and some observations that are needed to be kept in mind when talking about direct current systems. Now, this probably comes as a surprise. There is a legend that Professor Kröger at TU Delft started his lectures on high voltage DC with this statement. Now, why he would do that? In high voltage DC, and he was a pioneer of the topic, the partial discharges are extremely important. Now, the partial discharges occur especially when we have changes in the amplitude. And this statement holds very much true. The reason is that in DC we have the switching devices like converters. We have all kinds of overvoltages after dropping loads. We have many other things that are making DC many things but DC. And this is why it's important to think about this when designing the protection of the DC system. Now, when I talk about DC system, what I mean is a system like we are looking at now. The system usually consists of one or multiple sources for redundancy reasons. It very often has localized production through PV and usually has also battery energy system. Now, what you can see here is that the protection is provided not only through electromechanical switches or not only through fuses, but also through semiconductor devices. And you might be wondering why is that necessary, and I will explain that later. However, one other thing is we don't need them everywhere. So we need to design the systems and divide it into sectors and decide what type of protection is appropriate for the sectors. Now, this outlook is based on one of the industrial alliances, and there can be some other, but what they have usually in common is that the system is split into zones or sectors, and that is utilizing smart breakers or solid-state circuit breakers to connect these systems. What is influencing the choice of the protection in DC are the grounding schemes. Now, in principle, the grounding schemes in DC are very similar to AC, but it still makes of an interesting discussion to have a look at these options. The first option is the grounded system on the AC side. So in principle, we can have a transformer that will be Y connected, and the ground will be connected on the DC side and then used across the DC system. This is possible as long as we have a very small DC system, and at the same time, if there are no other AC loads on the secondary side of the transformer. If there are, or if the DC system becomes large, the difficulty becomes in the currents that are circulating through your earth, and this can lead even to corrosion in the building. So this type of grounding should be reserved for the very, very small systems done in DC. The second option that is more popular sure, my computer froze. This I apologize for the inconvenience. Oh, here we go.
Ja, wat techniek hè.
Ja, die kunsten in de dingen, dat is te halen.
Just a second, I have to turn on the PowerPoint. Ah, here we go. It's coming back. It's interesting. Okay. And here we end it. So I will share my screen again. And we can continue. So the second option is using IT systems, so essentially high impedance or ungrounded systems. These systems are the most popular, normally are deployed also with installation monitoring. You can see that one of the key things is that now we have the semiconductor device only in one of the polarities. And here it's important to distinguish because we have the electromechanical device that provides the galvanic isolation, but we have semiconductor device that provides the short circuit current interruption function. The third option, and that is the most complicated, is using a midpoint that is grounded and loadable. In this case, we need a more complex protection devices. At the same time, we need to think about balancing of the voltages on both sides. Otherwise, equalizing currents will flow through the neutral, and the neutral might not be designed for such operation. That's why these systems are usually more theoretical, and in practice, the DC IT systems are dominating. A critical aspect of designing a DC system is how we control it. Now, I mentioned that DC is not only about DC, and this is why we usually talk about voltage bands. Here we have an example of a voltage bands defined by ODCA, which is one of the industry alliances looking into DC. You can see that different devices connected to the DC grid can have different voltage bands in which they must provide the full functionality, where they can provide limited functionality, and where they must disconnect. Now, how all these converters agree who should provide current? Because you can imagine that when I have multiple sources, they need to know who and when is providing how much current for the load. And the answer to this question is the loop control. So the loop control is usually implemented in your converters. For example, if you have a drive converter, you can set the loop coefficients, which are essentially artificial or synthetic resistances that will define how much current will flow out of the source given the voltage. And then for the energy storage, photovoltaic and active in feed, you decide how much current is each providing in different sections. So that, for example, when we have very high voltage, because there is a lot of the sun, then for sure we will be charging the energy storage. At the same time, when the voltage becomes too high, we will also curtail the power provided by photovoltaics, and we will feed back to the grid if necessary to ensure that the DC system voltage does not go too high. If it goes too high, then we need to disconnect. So an important piece of the equation are the droop curves. But that's not all. The droop curves are usually provided on the very low level, or essentially in the converter, but it is not enough. We also need to think about the energy optimization, and that's why we have also tertiary level control, which is typically centralized, and this is where we do our energy management. So we go from the current and voltage loops that are deployed in the converter all the way to centralized controller that is making sure that the grid is operating at the most efficient point. Of course, the tertiary level is not required technically. However, it can make the utilization of your assets much more efficient. Now, one of the things that people are always afraid about is the protection of the DC systems. This is not surprising. I mean, there is not so much experience, and as well, there are not that many devices, as at least that's usually claimed. When we look at the standards, there is one relevant standard at the moment that makes sense to look at, and that's the IEC 61660, which tells us how to calculate a short circuit current in a DC grid. Now, this standard was, however, designed for DC systems that usually consist of passive rectifiers, lead-acid batteries, and large smoothing capacitors, and not so many loads, and for sure not many active converters connected together. Now, what happens when we have a bit more complicated DC systems, like the one we were looking at, the grid response does not necessarily need to look like this. In fact, it can be underdamped, for example, in which case the growth of the short circuit current will be sharper and the peak will be faster. But at the same time, the current can drop much sooner, which means that your protection or the trip detection unit might be too slow to even detect that you had a short circuit current. So one of the things when designing the protection, you need to also think about these type of things. Other aspect is, how do we evaluate the short circuit on the output of the converter? And this is based, of course, on the standard, but we need to be careful in evaluating the right impedances. So the cable resistance and inductance, or the busbar resistance and inductance. So when we look at this as an example, how we can evaluate a short circuit in a DC system, we, in the first stage, after a short circuit occurs, the capacitor will react as the fastest. And what is going to happen, we are going to have a capacitive discharge, which is this first part. And you can see the peak is very high. In this case, it's almost 40 kiloampere, but in large DC systems, 500 kiloampere is not unheard of as a prospective short circuit current. But then it drops off very quickly. After the current drops, the voltage is dropping as well. Likely the under voltage protection of the converter kicks in and the switching stops. However, the diodes that we have here, here, and here will continue to conduct current, and we are getting to the secondary phase where the current is commuting to the diodes, and the diodes will then continue to supply the current to the fault. And we need to check if this energy is enough to trigger the fuse, or if the fuse I squared T is as specified by the converter manufacturer. One other aspect when utilizing non-isolated converters is also the capability to actually protect themselves from the short circuit. For example, when we have a fault on the low voltage side of a buck converter, we will still have, of course, the discharge of the capacitor, but then we will have a path for the current to flow through the freewheeling diode. On the other side, when we have it on the high voltage side, even though we turn off both switch 1 and switch 2, in the secondary phase, the capacitor of the load can start feeding the fault on the high voltage side, because the voltage here dropped below the voltage of the load. And this is why very often we need to consider bidirectional protection devices. So what are the devices that are available? The most standard device is, of course, a DC circuit breaker, which provides direct suppression of the fault. Now, the key for the operation of a DC circuit breaker is that the voltage in the DC system is is lower than the arc voltage. Otherwise, the arc will be not extinguished and the circuit will continue to arc. Now, this method is very reliable and very robust. However, it takes several milliseconds or tens of milliseconds in large system to operate. That's why for protection of large power conversion systems, what is very popular are fuses combined with switch disconnectors. A popular choice can be, for example, ABAT fuse, which is a very fast semiconductor fuse, often used in combination with DC side of a power conversion system. If we have a fast enough fuse, it will limit the first peak of the current and also the released energy. Now, the problem with the fuse, of course, is that as you increase the rating, current rating of the fuse, also the let-through energy of the fuse is increasing. And what can happen when you need a fuse for 1, 2, or 3 kiloampere, the let-through current of the fuse will be anyway the first peak, and the fuse, based on the energy, will react somewhere here. So also the utilization of the fuses has some limitations in these DC systems. Nevertheless, most systems can be designed using traditional portfolio. So here we have as an example the electromechanical solutions, the switch disconnectors that are used typically with a fuse, the circuit breakers that don't need the fuse, and contactors that can also be used with a fuse. And one of the advantages, of course, that they can be switched very often. So they can be good solutions for hydrogen systems or electric vehicle charging systems. As I explained, there are some challenges in the DC system, and just as a recap before we go to the next section, first problem is that the current is rising very, very fast. So we need to detect the fault quickly, and we need new methods for fault detection. Second problem is that we reach the peak current very quickly, and if the capacitor is the only source of the energy, the voltage will drop. So we have low fault energy threshold. When the voltage is dropping and we don't stop it, we will have a blackout. So we need to interrupt the fault very fast. And as I explained, bidirectional protection becomes a requirement in DC because we want to, for example, recuperate the energy. But if we put unidirectional protection, then we don't have the control in both directions for protection, and it becomes, again, dangerous. So for all these reasons, we also need some new technology for protection of DC grids. And the technology is essentially, instead of using electric arc to extinguish the short circuit, to go to semiconductor. Now, the advantage of using semiconductor as a current interrupting device is the limitation of the energy. So here we see, this is of course just qualitative illustration, that we have a prospective current, air circuit breaker will take some time, and even though it's current limiting, it takes too long. And then we introduce solid-state circuit breakers that take just a fraction of the entire time and release just a fraction of the energy. A solid-state circuit breaker consists of, let's say, 3 main parts. First, of course, is the semiconductor switches that are conducting the current in the normal state and switching it off during the short circuit. Then we need an energy absorption device, because as you can imagine, as the current is growing in the DC grid, there is inductance in that system. And the energy stored in the inductance or in the magnetic field is growing as well. And this energy needs to be released somewhere. And that's why voltage clamping is so important. Otherwise, you would have over voltages in the system each time we interrupt a short circuit current. And third critical part is still an electromechanical device. Semiconductors by themselves, they do not provide galvanic isolation. And just because the semiconductor opened, it does not mean the circuit is safe to touch. So we need to have integrated electromechanical switch. And of course, some control units that are important. What usually influences the performance of the solid-state circuit breaker is how we arrange the semiconductors in the main part. A very common arrangement is using anti-series combination of switches, or you can use a single switch and surround it with 4 diodes, so with a diode bridge. In this case, you have always in the path of the current multiple semiconductors. Now, in some applications, this is not a problem, but in applications where efficiency is the key, this becomes a problem. And that's why having an anti-parallel combination of reverse blocking devices, like shown here, can be very advantageous because the efficiency is highly increased. So when we look at the operation waveforms of a solid-state circuit breaker, we see that the current is flowing through the main semiconductor device. We detect a fault, and here it's important also to say that the fault detection period is mostly defined by the time we need to make sure that there is a short circuit. As I said, in DC systems, you will have a lot of interruptions, various currents. It can happen that because the threshold of the short circuit in DC is quite low, that also just some spurious or some switching event happens that increases momentarily the current above your threshold, but you should not trip immediately. So the time that you need to interrupt the short circuit current is very often given or dominated by the time you need to make sure that indeed you are in a short circuit scenario. After you are sure that you have a short circuit, you turn off the semiconductor, and this is typically very fast and happens within microseconds. When that happens, the current commutes to the voltage absorption unit, or the MOV, as a typical choice, and we have some overvoltage happening. But this overvoltage is, of course, limited by the voltage absorption unit. The time D is usually given by the circuit characteristic, because this is given by the amount of energy that you need to dissipate. So what are the challenges that we need to overcome when designing a semiconductor circuit breaker? So first of all, semiconductor itself. It's not particularly a good conductor, as the name suggests, and we need to think about the losses that happen in there and how we get them out. So we need to find the right balance between introducing extra losses and removing them from the circuit. Second, semiconductors, as I mentioned, they are not providing galvanic isolation, so we need to add it to our device. And third, but not least, is to integrate all of these functionalities in a footprint that's acceptable for the application and that will not take too much space. And the first IEC certified semiconductor is right here. It is the Sace Infinitus. The team that developed it, I think they can be very proud of their achievement, because they were the first to actually manage to get the proper certification as a circuit breaker, which means it can be redeployed in systems in the IEC world. Also, because of integrating all the functionalities, it can act as a circuit breaker, contactor, as a switch, or an isolator. It enables sustainable energy transformation because it enables the DC systems, or systems that are much more efficient. Compared to the traditional technology, it's approximately 1,000 times faster, needing on average 20 microseconds to interrupt the short circuit current. Now consider that normal circuit breakers need 20, 40 milliseconds, depending, of course, on the current rating. Compared to other semiconductor current limiters, it is extremely efficient because it's using proprietary reverse blocking IGCTs that were developed especially for this application. Because of the super fast speed, there is almost no arc energy, so the arc exposure is eliminated. And since we have moved the electrical operations to the semiconductor, the endurance was dramatically increased. So traditional technology needs replacement after a certain number of electrical operation. With the switching of the semiconductor part of the Sace Infinitus, this is no longer needed. When we look at the actual measurement, so how does it look like when this device operates, it's very similar to the theoretical picture that we've seen. The breaking time, the worst breaking time is 25 microseconds. It's also given a little bit by the system inductance. That's why it's a bit higher, but on average, it's below 20 microseconds. And because of that, also the lead-through current of this device is pretty much defined. Lead-through current is usually around 5 kiloampere, but never more than 6. And this, you can imagine, is also quite a difference when we have a fuse or an electromechanical device where we are never quite so precise with these lead-through currents. One of the limitations of every semiconductor circuit breaker is the sensitivity to the system inductance, or to the DIDT, so the rate of rise of current. Now, as I said, we need to be sure that we are switching on a short circuit current. So we introduce certain time in the circuit breaker to make sure that we have a short circuit. Now, if this time is too long, what can happen is that the breaker will no longer be able to safely interrupt the current. So when we compare the two breakers, or the two technologies, because we need both at the end of the day, the electromechanical circuit breakers are limited by their short circuit capacity, while solid-state circuit breakers are limited or defined by the amount of inductance in the system. If it's too low, then it can happen that the breaker is not able to interrupt fast enough. If it's too high, the energy that needs to be dissipated in the circuit breaker can be too much. So this is something to also give a perspective that one is not replacing the other, rather they are just complementing each other, and we need both technologies. And now just very briefly, because I see we are already at the end of the time, some of the DC tools and knowledge base where you can have a look for further information. Now, some of the people say, okay, we don't see many DC projects, so why? Well, one of the arguments is, of course, the products. It is indeed true that the product portfolio of even the large players like Schneider, ABB, Eaton is now just building up. However, there are already some good products, and we had just looked at a few. Then the standardization is still somewhat limited. I will talk about it, but there are not that many standards as we have for AC, and therefore it's somewhat harder to design these systems. But very often what is limiting is the soft cost. So these are the costs of having the engineers educated, trained, and with the right tools that they need. And this is why, of course, ABB tries to promote activities like KIVI, but also other webinars. What we also try to do is publish the knowledge that we have. So you can download from our web pages the application notes that are discussing the protection of low voltage DC systems, or that are particularly talking about protection of power conversion systems with large DC buses. Recently, we have published the technical application paper on protection devices for current applications. I highly recommend downloading it. It is almost a book of around 80 to 100 pages of good theory behind DC systems and the protection devices. There are also some tools that I would like to bring your attention to. This is not an ABB tool, however, it's an interesting tool where you can design DC microgrids and size the cabling and do power control designs quite easily. And there is a large library of off-the-shelf devices for both the power conversion and also the protection. Last but not least, if your company or you yourself are interested in the topic of DC, there are two industry alliances that can be of interest. One is Current OS, originally, as a matter of fact, started in the Netherlands. Currently, the board members are also added with Mersen, a French fuse manufacturer, and many other members from various industries. By now, actually, because this number is already 2 years old, it's almost 100 partners in the Current OS associations. And the universities can join the Current OS association for free. The second association started in Germany with more focus in the industries. Today, it has also around 80 to 90 partners. And this association is a little bit more focused on applications that have large motors or robots, and a little bit less focused on the applications, for example, as an EV charging. However, also very interesting. And one of the big advantages of ODCA, if you go to their webpage, you can download for free the DC Industry 2 system concept, which is a material that describes the DC systems. Now, I described two alliances. What are the differences? Of course, there are some, but the basic principles are very similar. It's always voltage-controlled networks. The energy management or the grid management is distributed, so they are describing the droop characteristics, and the protection is done through sectors and zones. And with this, thank you very much. It was a pleasure to be with you here today. And as our new logo goes, engineer to outrun, everything that's designed to run smoothly can be designed to run even better. Thank you very much.
Thank you, Pavel. Thank you for your time, and we have now time to answer some questions. Thank you very much for your interesting presentation. I haven't seen lots of questions in the chat. Maybe they will come now. Have a look at it. There you are. And I will start with some questions. Even kijken. A typical Dutch question I saw. was what's the difference between the costs of the safety devices between AC and DC?
Okay, so I don't think there is a big difference when we look at the electromechanical devices. Of course, you know, there are different types of fuses, different ratings, but this is within the same order of magnitude. Probably you are asking about the solid state protection. Of course, that's a bit more expensive, but you have to consider that it's a little bit like comparing a cost of a power converter with the cost of a switch. In a solid state circuit breaker, we have the semiconductor part and we have the electromechanical part, and neither comes for free, but we need to put both of them. So this will drive the cost or the price of the device. But this is also what I mentioned at the beginning. You know, we are making the components a little bit more complex, but the system we are making simpler. So the hope is that the number of devices goes down, and that's why on the system level, it should come as an efficient solution.
Yeah, same as the battery prices. Right. The next question is from Gerard Vromans. How do you know if the semiconductors can survive the short circuit generated from the grid of the source, or is the intent to replace the semiconductor?
No. So this is the cool thing about the semiconductors. They are so fast that the I²T doesn't have time to build up.
Okay.
We detect the fault very quickly, already at the lower magnitude of the current, and we switch within a few microseconds. So the I²T, you know, it's like compared to a fuse, it's not 100 times smaller. It could be easily 10,000 times smaller depending on the rating. And this is the consequence of what I said. You define the lead-through current. So you know what's going to be the lead-through current through your semiconductor protection device. So as a matter of fact, you don't need to replace it. It can survive many short-circuit events.
Yes, right, okay.
It doesn't age.
Good. Gerrit has another question is, how do you achieve section discrimination upstream if you use ultra-fast switching, or is there a different design thought applicable here? If you you explain?
Yeah, so this is a little bit more challenging in DC than in AC, also because think about it, it's not only your source supplying the short circuit, but also your loads will start discharge. So you have contribution from different parts. And as a matter of fact, in different applications, we do it differently. Very often, for example, in marine, what you do, you have segmentations into sectors, and you switch off a sector, but you interrupt in between the sectors very quickly to ensure survivability of the other sector. So this is the very basic, but this is more on the sensitivity of the protection devices. Then you can have a closed bus and have multiple breakers operating together, and then you need to coordinate. And this is very often where communication comes into play. There are some other methods like similar to differential and I don't know what, but they are more, again, theoretical. You can find them in IEEE publications.
Okay. Next question is from Arend van der Velde. How to maintain the infinite DC, let's say after 5 or 10 years?
Okay, to simplify, I will talk about 3 main things that need maintenance. One is the liquid cooling. I didn't mention it, but Infinitus is liquid cooled. It's essentially a system for up to 3 megawatts. So we need some sort of a cooling. Liquid cooling needs some maintenance in a regular interval. These are, let's say, the connections. This is less than 5 years. I don't remember exact time. The semiconductor part has a lifetime of 10 to 15 years. None of them are in service for 10 years because they were essentially introduced last year. But this is the estimate. It is on the other hand, it is a well-known semiconductor, so there shouldn't be many surprises. And what needs maintenance is, of course, the mechanical part, so the switch disconnector. And this has the same maintenance intervals as other electromechanical devices, but they are also application dependent, right? If I don't know, if I put it on a vessel, then I need to check the screws and so on regularly.
Yeah. Okay. You mentioned the DC lines needs less copper. When we turn it around, can we use the current high voltage power lines to transport DC with a higher total power? In other words, use the current lines to transport more power.
That's a nice
Yeah.
question. But funny enough, it comes back to Professor Kruger and partial discharges. The problem you will run into is the aging of the insulation. The reason probably why you cannot do it so simply, even though you have the right number of wires inside, is the insulation. So it sounds like a good idea, but probably the insulation is what would stop it.
But then we can't use the current grids for DC.
For high voltage DC, as the question suggests, this is probably not possible. There were some studies done for low voltage where the insulation is not such a critical topic. And there is some results that I have seen. Now I have a bit hard time remembering let's say the concrete study. I just remember a presentation that I've seen that suggested that you could use the three-phase wires. The third wire could be used as a grounding. So they suggested it's possible, but again, this was a study published in IEEE with some testing, but as an engineer, we should require a bit more than okay. Some researchers did a study and they tested it somehow in the lab, so it can be tricky.
Yeah. Okay. And then another question from Gerard Vromans. Do makers max supply 12T capability or semiconductors publicize as they don't know?
So I believe normally when I buy, let's say, a converter, it comes with an I²2 energy because I need to choose the fuse for the DC side. For solid state circuit breakers, I don't think we, for example, have now, because of course, as I explained, for the current, we have the lead through current, so the I²2 we limit. And I believe in our data sheet, but I will have to check, there should be the maximum inductance of the line. So that it's not recommended to switch inductance higher than X. I don't remember the number, but it's ridiculously high, honestly. Otherwise, the MOV would be too small. This could be a challenge for, you have a small circuit breakers for 1632 ampere that don't use MOVs, but for example, TVS diodes for the voltage suppression, and the TVS diodes are sensitive to this. So then it becomes an important parameter, but there are not that many of these small breakers because the value proposition is a little bit tricky.
Okay. I have another question from Verder Hiemstra. Now we have the North Sea wind parks. I understand most of them will transport energy DC to land. Are there initiatives to extend that transport for distribution on land?
I am not sure. When we go back to the, I was showing the grid picture. We have the HVDC on the generation side, of course, and then the DC project I was talking about is the grid edge. So it is where, the TSO, like Tenet, is not so interested, or Stedin as a DSO example. Now, that being said, when I was studying in the university, in my research project, Stedin was one of the stakeholders. So they were interested for sure in the technology, and they were joining our meetings and giving us feedbacks on how things actually work. Same thing in France, EDF is part of current OS, and they are a very active part of current OS. So I think on the short term, I would be surprised to see an actual deployment of DC in distribution level. So front of the meter application. But that being said, the companies that are managing these grids and building these grids, they are looking into this topic. So maybe they are considering some pilots, and we could see them in the near future. But I don't know anything concrete.
Okay. Another question from Gerard Vromans. If you in time expand the grid with users with capacitors in the DC, and how do you know if the old design still fits? As we have no control over the expansion of the grid.
Yes, and this is especially a problem if you would go to distribution level, right? As I said, most DC systems and applications are greenfield applications or closed systems, and the expansion is not done, or when it's done, then it's done through sectors. So imagine that I have a DC sector, and then when I want to expand it, I build another DC sector, and when I need to interconnect them, I will interconnect with solid-state circuit breaker. In that case, this problem is taken care of. So this is one way to expand, but indeed, it is something that's that so far did not attract so much attention because of where these systems were deployed.
I have no more questions in the chat, but I myself have questions. How do we go from here? What can we do with the energy transition? And we will use the DC as an opportunity. How do we go from here? You said the product, the standardization, and the education are aspects. But where do we start? What can governments do, or where is the ball?
Yeah, so I think there are some segments where DC is already well established and it's growing on its own. I'm thinking marine. There are other segments like buildings or industry, where we need. So for industry in particular, we need to run the pilots a little longer because we did the pilots with the engineering designs, but now also the people who do maintenance need to get a hold of the topic. So this will take a little time. And other thing is there are many opportunities popping up now with all the battery energy storage that's being installed. If you are installing battery energy storage and PV and co-locating them, you anyway can use the DC bus. If you have the DC bus there, why not think about expanding it further? So this is another opportunity. Of course, it would be nice to have, for example, I mentioned in China, there are many projects, especially these PEDFs. One of the reasons is that there is incentive from the government to support these solutions that should help with the energy transition. And then there are other applications such as data centers, and they will probably go their own way because they are already economically feasible. So there are some applications where some support is needed for the market, and some where it's already growing quite well.
Yeah, but you also need some time to get more experience with the maintenance. How long does semiconductors go with? You said 15 years, but is this 15 years, or is it less, or is it more? Lifetime?
I don't know, but also I think very often we hear about the adoption rates of software products. How long did it took for a phone? How long did it take for AI to take over? This is fast because you don't need to build infrastructure. We are in infrastructure game essentially. And in infrastructure, we are doing lifetime projects, right? So it will grow, but the rate will be as we see in other infrastructure fields.
Okay. I have a last question from because it's past 1 o'clock from Gerard Vromans. Would voltage discrimination not be a solution for the national grid?
I don't know. I don't feel confident answering this question because this is maybe more on the engineers from. I have power electronics background. Of course, we had studies in power systems, but I would say, as my old boss used to say, I know enough to be dangerous. So I will let more competent people to answer this question.
Okay. Right.
Thank you very much.
Thank you for Pavel, thank you for your time and knowledge for today's webinar. We will present our appreciation by a digital present, which will be sent to you shortly. On our next webinar will be the 17th of September this year, and will be about the electricity system in transition demands a new strategy for success, by Wouter Leijbrand and Helene van der Veen, both from TNO. On behalf of KIVI, I would like to thank everyone for their interest, and we hope to see you again in the future, e-lunch webinar or another activity by KIVI. For now, we wish you a pleasant day and request you to close your team connection and leave this meeting. And Pavel, can you stay a little longer, please?
Yeah. Thank you very much, everybody, for joining. It was a pleasure to be here. Thank you.